Okay, I'd like to continue with the final exam review for Math 1033. We're going to look at question number 27, which is an equation involving fractions. So if you'll take out your paper and follow along with the problem, I'd like to go ahead and bring you down to the piece of paper with me so that you can see the problem and watch me work it for you. All right, let's get the camera focused in on the problem. Okay, so notice problem number 27. We have the equation x plus 1 over 5 minus 1/3 is equal to 2x minus 11 over 15. Now, one of the biggest things in this problem, one of the annoying parts of this equation, the way it's written, is that you have those fractions to deal with. So one of the things I try to tell my students in class is when you're solving an equation that has fractions in it, your first goal is to make those fractions disappear. So in this particular problem, I would look at every denominator. I would look at the 5, I would look at the 3, I would look at the 15, and I can tell that the LCD is 15. So what I'm going to do is I'm going to go to each part of this problem, and I'm going to do what I call BAM. BAM, multiply by 15, BAM, multiply by 15, and BAM, multiply by 15. Now sometimes it's easier to write 15 as 15 over 1 because it makes some of the multiplying easier to see. So follow me on to the next step. We found our LCD, which was 15. We multiply by it. 5 cancels into this 15 3 times. Now something that's very important to remember, this 3 is not just multiplied by x, but it's also multiplied by this positive 1. And sometimes what's real helpful to do when there's more than one term in a numerator is to put parens around it so that you remember to distribute. Putting those in can really help you. Sometimes I call those safety nets. So now when I distribute, 3 times x is 3x. 3 times positive 1 is a positive 3. The next multiplication, 3 cancels into the 15 5 times. Negative 5 times 1 is negative 5. Now notice in this problem we didn't need safety nets because there was only one term in the numerator. We didn't have to distribute, so the safety nets would have been kind of stupid. Over here, the 15s cancel. Technically it goes into there one time, but basically they're gone. So on this side of the equation we are left with 2x minus 11. Now before we continue with the problem, let me back up here with the camera. Notice how much prettier that problem looks. We have no more denominators left. It's basically a one-liner. So now it's pretty much home free. On the left-hand side of the equation we combine like terms, which is going to result in 3x minus 2. Don't forget your equal sign. On the right-hand side of the equation we have 2x minus 11. Now remember the goal here, since this is a linear equation, a first-degree equation, get your variables on one side, get your constants on the other. I'm going to get my variables on the left-hand side of the equation, and I'm going to get my constants over on the right. You can pick any side you want to, but you've got to have a plan to work with. If I want this side of the equation to contain variables only, I'm going to undo the minus 2 by adding 2 to both sides of the equation. If I want to get my variables not on the right but rather here, I'm going to undo this 2x by subtracting 2x from both sides of the equation. And when I take a look at what I have, here's my equal sign. Always remember to put that on the left-hand side. When I collect like terms, the left-hand side simply combines to x. And on the right-hand side, I end up getting negative 9. My answer to this problem is x equals negative 9. One of the main reasons that I don't need to actually officially check it is if you look back at the original problem, there were no variables in a denominator. Every denominator was a constant, which means there's no way those denominators are going to become 0, so you don't officially have to worry about checking your answer. The solution set to this problem would be the set containing negative 9. Part of why this is pretty consistent with equations in general, look at the original problem. Each one of the x's was raised to the first power, so this was a first degree equation. And a lot of times the degree of the equation tells you the number of solutions. One solution, degree 1. Now it's not always the case, but it's a good thing to look for.